Hi, I'm Patrick.
I'm Liam.
And I'm Daniel.
And today we're going to take you through the design, creation and testing of our super handy handbot.
We created this robot as part of our implant engineering classwork in our biomedical engineering course. Our task for this project was to receive a 3D printed prosthetic called the Phoenix Hand version 2.0 and adapt it to become something both functional and creative.
The main inspiration for the direction we chose to take with our hand was the game Surgeon Simulator. In this game, the player plays as a hand which they can move around the screen using the mouse. They can raise and lower the hand and flex or extend the fingers as needed to grasp objects in order to perform different types of surgery.
We decided that we wanted to make a device that simulates this game as closely as possible, meaning the hand needed to be able to move precisely in 3 axes, the fingers needed to be able to open and close, and a camera needed to be able to see what's going on. As well as that, we wanted our course coordinator to be able to play the game from her house over the internet.
Our entire design is inspired by a robot created by the YouTuber James Broughton. You can see that his result is very similar to ours in terms of function, but in order to accommodate for our different needs, every single component from James's design had to be remade from scratch. Our design takes the original 3D printed hand model that we received from RMIT at the beginning of the group project and adds an arm to it to allow it to move in the directions we need it to. As seen in this CAD model, the arm is unlike a human's arm and instead functions with multiple elbow joints with which the hand is attached to at the end of. This allows the hand to move in both the X and Y direction. The arm is attached to a carriage that moves along a rail that operates with a 360-degree servo motor, a drive belt and some custom 3D printed gears. This allows for the arm and the hand to move freely in the Z direction. The final segment of the arm that is attached to the hand has a servo which pulls onto the strings that act as tendons to open and close the fingers. The movement of the arm, track and hand is completely reliant on high torque servo motors which rotate and move the arm in accordance with the input program. We chose to use 12 kg/cm HXT12K Metal Gear servos instead of relying on the weak 9 g/cm motors we received from RMIT. The weight of the servos on the arm component meant we needed to take in consideration the center of gravity of the arm. To solve this design issue, we had the servos and the joints alternating sides of the arm in order to keep the center of gravity directly over the carriage.
The functionality of the design is dependent on the user's input on the front end. In this case, a website that allows the user to manipulate the position and movement of the arm through their keyboard inputs. This website consists of a COM port selection dropdown, a command interface, a coordinate display, and a live camera feed. Depending on this dropdown here, the user will either have control over the angle of the servos or the position of the end effector using the WASD, Q, and E keys on their keyboard. The camera feed allows the user to be able to see the arm itself and its response to the user's input, which enhances the video game concept we are aiming to achieve. The coordinate display shows the angles of the arm servos in a manner that is easy for the user to understand. Movement of the arms can be controlled via keyboard inputs and their effects can be seen in these little bubbles. The servo controls have limitations built in to prevent any sporadic movement, restricting the user from being able to move the servo below 0 degrees and above 180. The COM port dropdown allows users to select which communications port the Arduino is connected to on the host computer. This means that theoretically multiple devices could be connected to the computer and controlled by one interface, giving us further future expansion options.
Alright, so now that we know how the whole thing works, here's some footage of us actually putting it together. The code for this project took even more time to get right than the design. The scope of the project means that there are many different sections and pieces of code that all need to work together in tandem to make a good final product. The system that we used for the code is as follows. On the host computer, a node server is running with three main modules. It uses OpenCV to capture video from the host machine's camera, Socket I/O to send and receive data from the client, and Serial Port to send and receive data to a connected Arduino via the UART communications method. On the Arduino is a very simple piece of code that reads in data from the serial stream. This uses a custom method other than the basic serial.readString or serial.readInt, because those methods are very slow due to the fact that they have to read the entire length of the serial buffer. Instead, our code looks for a starting character, reads the integers after the character, and then stops when it sees a return character. This means that it no longer has to read the entire buffer to understand the string, only the characters that it needs. Once the Arduino reads the input string, it writes the integer of the string to the servo specified by the starting character. In this case, it will write the angle 32 to servo A. The next section of code is done on the front end. The front end itself is a website I designed which allows the user to interact with the robot. It displays the current angle of all of the servos, a camera feed for anyone playing over the internet, and allows users to send commands over the Arduino via text box or control the angles using the keyboard. Behind the scenes of the front end, the state of the arm is stored as a JavaScript object, with a key for the current angles of each of its servos and the current X and Y position of the end effector. When a change is made to the arm, say if the user presses the W key, then this object is updated with its new values and is sent via WebSocket to the server. The server then reads these values and identifies the differences between the old position and the new position. It then sends the commands to the Arduino that are needed to achieve the new position. The host site also has an inverse kinematics function that takes in an X and Y coordinate and outputs the angles that the server needs to be in for the end effector to be at that position. The mathematics for this is displayed here on this Desmos graph. Since we know the target position, as well as the length of the arm segments, we can create a triangle between the origin, the joint, and the target. We can then deduct the angles that servers need to be in using simple trigonometry. To get the camera to work, the OpenCV module was used on the server side to record a video stream from the server machine's camera. This video stream is then sent frame by frame to each of the hosts using WebSockets. This method of streaming video is somewhat suboptimal and has room to be improved. However, there were more important things in our code that we had to optimize before the video stream.
So finally, here's what a robot can do. In angle mode, W and S control the base angle, A and D control the joint angle, and E and Q control the wrist angle. In position mode, W and S control the up and down position of the hands, and A and D control the forward and back position of the hands. This mode uses the inverse kinematics model to calculate the angles of the servos based on this X and Y position. In either mode, when the user presses the J and L keys, the robot moves left and right along the rail, and when the spacebar key is pressed, the robot clasps its hand. When controlling the arm from the computer hosting the server, the user has real-time access to the arm's movements with almost no latency. When controlling the robot over the internet, the user still has full control, however there is significantly more latency, sometimes up to multiple seconds. This is because we are hosting the server on a non-dedicated, non-optimized machine. This could somewhat be fixed by purchasing a dedicated server and using a service such as Google Cloud Compute.
In the end, we believe their final design and product upheld the expectations we set going into the project. The arm is able to move in all directional axes as planned, the hand can be open and closed, and all of it is able to be controlled wirelessly over the internet.
The end user experience is pretty much exactly what we are going for. It simulates the game Surgeon Simulator, and it's fairly fun to mess around with. We even ended up giving our course coordinator a go, and it's safe to say that she had lots of fun.
The whole term credit.
You've done a really good job, guys. No, I think you've gone above and beyond.
Creating this device was certainly a challenge, but a fun one at that. It involved coding, CAD modeling, designing, and hours of frustration, but in the end produced something we could all be proud of.
Hopefully you've enjoyed this video and have gotten a good idea of how our project panned out. I've been Patrick,
Liam, Daniel,
and we'll see you in the next one. Perfect, that's it.
That's the one.